Okay, so you guys have a question on your homework assignment that unfortunately I was not able to cover the material for during class, and I think Dr. Schindel was not able to cover the material in his section. So I thought I would give you a quick video with an example problem that illustrates how to do the problem that is on your homework assignment. So this material has to do with this idea of relative velocity. So you'll want to read the relevant section in your textbook in chapter 3. Okay, so in this example, we imagine that there is a swimmer, let's say Michael Phelps, okay, and he wants to cross the Mississippi River, okay, and he's going to start on one side of the river, and his goal is to cross all the way to the other side, exactly on the other side. So he wants to go perpendicular to the riverbank, crossing to the other side. And we're going to assume that the river is 100 meters wide. And that's going to be, we're going to call that distance delta y. Okay? And we're going to assume that he wants to cross the river in a time period, delta t, of 50 seconds. Okay? 50 seconds. And the river is not stationary, it's a river, so the water is moving, and we're going to assume that it's moving to the right at a speed v river, vr, and this speed is 1 meter per second. Okay? Now, Michael Phelps cannot just swim straight across. If he swims straight across, the river is going to carry him downstream. So what he has to do, he has to angle his swimming off at some angle. We're going to call that angle theta. And we're going to call his speed relative to the water v Phelps. Okay, so Vp. And the question is, given what we have here, what is v Phelps, and what is this angle theta that he has to swim at relative to the vertical? Okay, so in this problem, this is really a problem about vector math, because Vp is Phelps's velocity with respect to the water, relative to the water. But the water is moving relative to the ground. And his total velocity relative to the ground needs to be straight up so that he can cross this river, going perpendicular to the riverbanks. So there's a vector equation, there's a graphical representation that relates the three important vectors that we have. The vector that I didn't draw in this picture is the total velocity. So the total velocity needs to be straight up. V total. So graphically, the relationship between these three vectors is that we have V Phelps this way, we have V river this way, and we have V total going straight up. Okay? So V Phelps plus V river, notice these are tip to tail, must give you the total velocity. So if I write that as a vector equation, I have V total vector equals V Phelps plus V river. Okay? So if we want to know what V Phelps is, the magnitude of Michael Phelps' velocity, his speed, okay, what we want is this, that's the magnitude of this vector. And we want to know the angle, then what we'll want to do is write these three vectors in component form in terms of the relevant unit vectors. So let's do that. let's see what we can come up with here. So the first thing we can do is we can write v Phelps in terms of his unknown speed and this unknown angle in terms of the unit vectors. So v Phelps is going to have an x component and a y component. What is the x component? Let's take a look at this. So v Phelps kind of, it goes off like this, right? v Phelps, and its x component is the horizontal component, and its y component is this vertical component. So this is the angle theta. So looking at my trig, I have that the horizontal component points to the left, so it's negative, and its magnitude is this speed times the sine of theta. So Vp sine theta, okay? And that's the x component, so then I put an x hat here. The vertical component is positive, it points up. And so I put a plus sign here, and it has magnitude Vp times the cosine of theta, y hat, okay? Cool, so now what about the other vectors? Now Vt, the total velocity of Michael Phelps relative to the riverbank, that's straight up. So Vt is, well, what is its size? How long is that vector? Well, he needs to cover this distance, 100 meters, in a time, 50 seconds. So velocity is going to be, his velocity is going to be 100 meters divided by 50 seconds. So delta y over delta t. I'll plug in the numbers later. And that's in the y hat direction, and it's positive because he's moving up. And then finally, v river. V river is moving to the right. So that's going to be plus 1 meter per second. Again, I'll plug in the numbers later. Let me just make it VR and then x hat. Okay. Okay, now we can plug into our vector equation that we have here. Okay, this is the relationship between these three vectors. So, v total is delta y over delta t y hat. Now that's got to equal Vp, which has these two components, minus Vp sine theta x hat plus Vp cos theta y hat plus Vr. Now Vr is plus Vr x hat. Now this vector equation gives us everything we need. And the key is that the x components have to be satisfied separately from the y component. So what I could do is I could collect the x components on both sides and the y components on both sides. If I just write them together, collecting the x components here, I have minus Vp sine theta plus Vr x hat plus, now the y component, Vp cos theta y. And on the left side, I still have delta y over delta t y hat. So on the left-hand side, there is no x component. So the total x component on the right-hand side here better be 0. So this stuff better be 0, okay? All of that needs to vanish. Let's see if I can get a better marker here. So all of this stuff better be 0, because there's no x component at all on the left side. Meanwhile, this better equal this. The y components on both sides need to be equal to each other. So I have two equations. in the x direction, I have that this thing needs to be 0. Well, what does that mean? That means that VR needs to be equal to VP sine theta. So I have VR equals VP sine theta. In the y direction, I have delta y over delta t equals VP cosine theta. Now I have two equations and two unknowns. My two unknowns are VP and theta, and these are my two equations. Okay. Okay, cool. So now there's two ways I could do it. Probably the simplest thing I could do in order to find theta is to divide one of these equations by the other, right? So what I'm going to do is I'm going to take this equation, this first equation, and divide by this second equation, right? So let's see what happens when I do that. So I take the left-hand side, and I have VR over delta y over delta t. Okay, so I have VR divided by delta y over delta t. That's just this divided by this. Well, that better be equal to this divided by this. Now the VP's cancel, and sine over cosine gives me tangent. So tangent theta. Okay? So that says that theta is the arctangent of VR divided by delta y over delta t. Okay, so VR was 1 meters per second, and delta y over delta t was 100 over 50, so that's 2 meters per second. So this is the arctangent of a half. And the arctangent of a half, all of this stuff inside gives me a half, and the arctangent of a half is about 27 degrees. Okay? So that's one answer. Let's box that. And then, in order to find the magnitude of Michael Phelps' velocity, his speed, what I need to do is plug this into one of my other equations. So I could use either of these because I know the left-hand side of both of these things, and now I know theta. So let's just use the x direction equation. So then I would get VP equals VR divided by the sine of theta, which is 1 meters per second divided by the sine of 27 degrees. And so that is roughly 2.24 meters per second. Okay? Okay, cool. That's it. So just to review real quick, what are the highlights of how to do these kinds of problems? You want to make sure that you draw the right vector diagram. So really, a diagram like this one. Now in your problem, marker doesn't work. In your problem, you may not have a diagram exactly like this, but you will always have 3 vectors that will need to be related to each other according to some vector sum like this. It will always be the total vector equals the velocity of the moving object with respect to the fluid that's moving. That could be water in this case, or it could be air if you have an airplane or something like that. And then you have the velocity of the moving fluid relative to the ground. And that gives you the velocity of the moving object with respect to the ground when you add those together. So set up the vector sum, draw the picture, do the trig, okay? Represent the vectors in component form, and then set up the two equations, two unknowns. Okay? Great. Thanks for watching.